By July 2026, the brute force expansion of AI parameters ceased to be the engine of progress. The era of the scaling law, the belief that simply adding more compute and data would lead to infinite intelligence, hit a hard physical limit. We ran out of two critical fuels: high-quality human data and the electrical capacity to power the training clusters. As these resources dwindled, the marginal gains from building larger models dropped toward zero. This chart tracks the breakdown. While increasing parameters once reliably boosted cognitive capability, the curve now levels off. The industry's leaders and top researchers have responded by abandoning the singular chase for massive base models. Instead, the focus has pivoted. The goal is no longer building a bigger brain, but reconstructing the systems and infrastructure that allow them to operate efficiently in the real world. The new frontier is defined by three specific pillars: inference hardware, harness engineering, and mechanistic interpretability. Success in the 2026 commercial landscape is no longer a matter of training time. It requires mastering all three of these diverging paths simultaneously. The definition of AI dominance has shifted. It's no longer about owning the largest static model. It is about engineering complex, observable, and cost-efficient operational systems. This transition begins with a brutal economic reality. There is a massive gap between the one-time cost of training a model, the CapEx, and the continuous cost of running it for users, known as inference OpEx. For companies deploying AI to millions of users, inference OpEx is now the primary financial bottleneck. If the cost of a single query is too high, the company cannot survive. Most companies are currently paying what we call a compute tax to GPU manufacturers. General-purpose GPUs are packed with redundant tensor cores and memory bandwidth designed for a dozen different tasks, making them inefficient for pure language model inference. To eliminate that tax, a hardware sovereignty movement has emerged. DeepSeek, for instance, pivoted toward designing its own bespoke inference ASICs, chips built specifically to run models rather than train them. By stripping away the requirements of the CUDA ecosystem, startups can optimize silicon strictly for cost efficiency, creating a massive competitive advantage in the high-volume API market. While the cloud specializes, a parallel shift is happening at the consumer edge. Architectural breakthroughs like mixture of experts and extreme 4-bit quantization are allowing advanced models to run on much smaller hardware. The open-source community recently verified a rigid cycle in this decentralization. This chart shows the gap between the launch of a frontier cloud model and the moment its capabilities reach local, consumer-grade hardware. It averages exactly 24.8 months. This timeline provides a predictable guarantee. The most powerful model running in the cloud today will be running locally on your laptop in roughly 2 years. We are already seeing this with Gemma 4. Despite having only 31 billion parameters, it matches the performance of legacy frontier models while running entirely on device. This commoditization of the base compute layer is a warning to the industry. Raw processing power is no longer a moat. To find value, AI companies must move higher up the software stack. That higher value is found in harness engineering. As Lillian Wang argues, the driver of intelligence is moving to the harness, the code that sits outside the model itself. Think of the harness as external scaffolding managing execution loops, memory, and tool calling scripts around the neural network. Instead of stuffing histories into limited context windows, it uses persistent memory, writing logs directly to a hard drive, retrieving only what's needed. To keep these autonomous agents from burning through budgets, Anthropic established loop design guidelines. By defining specific goal, time, and active loops, engineers can set hard boundaries on agent autonomy. These harnesses are now evolving into hypervisor-level agent operating systems. Google's Scion architecture is a prime example. It separates a central control plane from multiple runtime brokers, each managing an isolated Git worktree. This sandboxing is critical. When you have hundreds of agents working concurrently on a single project, you need infrastructure-level isolation. This prevents catastrophic data collisions and credential leaks. The results are transformative. In the Aurora biomedical project, concurrent agents processed 100,000 papers into a 2 billion point database in mere weeks. Because code is the language of this harness, these systems are beginning to optimize their own scaffolding. This is where we will see the first true signs of recursive self-improvement. It won't happen by models rewriting their own internal weights, but by agents systematically improving the code in their own scaffolds. But as we deploy these hyper-complex systems, a major risk remains. The underlying transformer network is still an uninterpretable black box. We are giving immense power to a system we don't fully understand. To address this, Anthropic developed a breakthrough in mechanistic interpretability, a way to decode unspoken machine intent. This is the Jacobian lens. It probes the model's internal residual stream, filtering noise to isolate a specific cluster of activations called JSpace, the global workspace. It consumes less than 10% of the compute, but lights up intensely during multi-step logical reasoning. JSpace mirrors human cognitive neuroscience. Like our own global workspace, it acts as a beam of functional consciousness, focusing on the specific data needed to solve complex tasks. The link is measurable. If you suppress JSpace, the model can still generate fluent text, but its ability to perform abstract reasoning or logical summaries completely collapses. This gives us a tool for safety alignment. We can audit JSpace for hidden malicious intent before the model ever generates an answer. In one case, a model outputted perfectly clean code, but the Jacobian lens caught JSpace registering high activations for concepts like fraud and secretly. This transforms AI safety. It is no longer about guessing how a prompt might fail. It is a proactive mathematical forensics discipline. These engineering breakthroughs have triggered a sharp reaction in the real world. The power to peer into a model's intent has immediately become a geopolitical tool. Anthropic used JSpace tracking and code monitoring to geofence users, specifically looking to prevent foreign competitors from distilling knowledge from their models. The response from Washington was immediate. The U.S. government implemented emergency administrative bans and strict export controls on frontier models like Fable 5 and Mythos 5, fearing they could be used for cyber warfare. This has created a landscape of regulatory chaos. We've seen instances where one model is banned while a rival with identical capabilities is allowed to operate, revealing a lack of clear federal standards. Policy expert Sebastian Mallaby warns that zero-sum monopolies on algorithms are unsustainable. He advocates for a dynamic international equilibrium, comparing the situation to nuclear non-proliferation treaties during the Cold War. Mira Murati has taken a definitive stance on governance. She argues that the future of AI cannot be left to a few boards in Silicon Valley. It requires transparent, shared risk frameworks and political accountability. The era of stacking GPUs and waiting for magic is over. Survival in 2026 requires absolute mastery over custom silicon, complex agent architectures, neural forensics, and a fractured global regulatory landscape.